Okay, so today it's sort of, I decided, yes, so I will follow this book and do this kind of naive intersection theory. I think this is a very good text, by the way. This Harris, Eisenbach-Harris. And then in the last 4 or 5 weeks, we'll discuss some, well, I don't know if more advanced, but more efficient in a sense, techniques using symmetries. So today I'll do a last sort of another application of the techniques. So we had, these were basically identification of Chow rings using Totaro's theorem, and then the theory of Chern classes, and them being clever. I mean, that's part of any mathematical technique that we have, right? So, so let me get back just for 1 second to the classification of, now you're all sitting there, so I can use a little part of this. Can I use this part, this thing also? This half, yeah? Because it's just sort of motivation, so I don't want to put in the main blackboard, but it's just the classification going back of plane cubics. You remember that one enumerative idea was that we calculated all the plane cubics, and they were parameterized by the coefficients of cubic polynomials in 3 variables. So there is it's a 10-dimensional space, so the plane cubics are thus parameterized by P9. So the cubics, all cubics, are parameterized by polynomials of degree 10 in 3 variables, right? So it's P9, and then by Bertini's theorem, we know that the generic cubic is smooth, and then there was a stratification of the singular ones. There is the biggest one, and the biggest one was a codimension 1 thing, and that was the nodal case. So we had the singular they are stratified by certain types that we discussed. I gave you a bunch of examples. The biggest piece was this codimension 1 piece. So the codimension 1 is something like something like this with a double point. So the largest piece is codimension 1. So these are nodal cubics. So the type of equations you see here is something like y squared equals, say, x squared times x plus t, if for t not equals 0. And so this will have a double point like this at the origin, right? So that's a typical thing. I wrote it this way because then you can also see that what happens if you set t to be 0, then you get already a singularity of higher codimension, which is a cusp. So that gives you the at t equals 0. This is a cusp of, then it's something like. Okay. So then what we were doing there is that we went higher down. We found a method using these gray type maps of describing the locus when the thing factors into 2 parts. You remember we had, for example, we looked at this situation, which is the same codimension as this one, in fact, as the cusps, when you have the cubic factors into a quadric and a line. And then the idea was that we just we used the map from the corresponding products of projective spaces, identified the image, and this way we could calculate the degree of the things. And so now I got to the part So one enumerative invariant would be to calculate the degree of the corresponding strata. So the main question, the enumerative question the degree of the strata. And so what it means in practice, I mean, just a simpler way of putting it is the following. For example, I didn't write it here, so this is the nodal cubics is the bigger piece. This is codimension. So e.g., for example, so the codimension of the nodal part is equal to 1. So this is, the whole thing is P9. So this is some 8-dimensional subvariety. So it's an 8-dimensional subvariety of cubics where there is a node, so which sort of look like this. But of course, the equation could be different, the point could be different where this node happens. And so the question is, so if it's codimension 1, then the question is, so this is the same question. If you take, say, 2 random cubics, these are now polynomials, cubic polynomials, and you construct a pencil out of that, so that will be a one-dimensional thing. So you look at, say, so you look at linear combinations. And so now you want these to be, you look in any linear family, the linear combinations that are nodal. Okay? So then this is codimension 1, and this is one-dimensional. So now the intersection, the number of intersection points will be precisely the degree, I mean, in a sufficiently general situation. So this is in the generic situation. So this is sort of a enumerative question we're looking for. And this we did solve with this method here. But for this nodal thing, this method does not work because well, it's not a product of any two things. It's irreducible, so we're not going to do this. So the idea is incredibly that actually the same technique as we used before, you remember, so this is a slightly different question. We then studied later of these extended objects like lines on hypersurfaces and things like that. We can use precisely the same techniques, and they work beautifully. So let's look at it. So the idea is actually very similar. The only thing we are going to do now is so I'll first format it maybe in just slightly more generally. So let's look at, let's consider now the general case. I'm going to generalize the plane to any dimension, and the degree is also to any dimension. Okay? So we are looking at degree d hypersurfaces. In Pn. So then, as just the same thing as we used before. So this is parametrized by some big projective space of coefficients, which was P9 here, and now it's going to be Pn. I guess n is n plus d choose n. Let me just check this is correct now. N, yeah, I think, yeah. And now in this space now we are looking for the hypersurfaces which are, so let's denote this by D. Now it's a definition. Let's just look at the spaces F such that, so the F Pn such that the corresponding XF has a singular point. Okay, so this thing is known as a discriminant. This is the discriminant. Now you've heard of the discriminant. The discriminant is in another setup, but actually it's exactly the same setup. So let's just look at the very, very simplest case. Actually, I'm just going to look in, well, just, yeah. The very simplest case is when you take, say, P2 and you took at degree 2 polynomials. So then you look at the situation ax squared plus b, sorry, P1, px plus c equals 0. And you're looking for combinations A, B, C such that this is singular. And of course, singular, now this is just a finite, it's a scheme of 2 points. So of course, it's singular precisely when the two roots coincide. And it's going to be a sort of a hairy scheme. So we are looking at A, B, C such that this is singular. Singular, which is the same thing as it says the quadratic equation as a double root. I'll explain in a second why that's the same, but I mean it's the same, right? Okay, and so that we know that this gives you an equation, a subvariety, which is just says that b squared minus 4ac is 0, right? So this is what you learn in elementary school, and so what we are trying to do now is to generalize this. So here we just want the degree, so the degree here is 2 actually. Yes, so you can see it's 2. Okay, so let's now go on and try to understand how to calculate. So the degree of D is equal to 2 in this case, and so we just try to calculate this number now for any D and N. That's the goal now. And so as I said, amazingly, the exact same thing works as before. We just need to get a little bit, write down more precisely what singular points are. So what does it mean that f, so this is now one of these polynomials, right, is singular at P? So in local coordinates, so when it's actually something very funny and beautiful happens in the projective case. If you just do it now first, suppose that, say, f in, say, let's look at just a very simple case, xn is singular at P in affine space. So then what does that mean? I mean, singular just means that, you know, all the partial derivatives vanish. This is otherwise, using the implicit theorem, the thing will be smooth. So this is if and only if the df by dxi at P are 0 for all I. And plus, we also want that f should be 0 at the point plus. Okay, so we have n plus 1 equations. Okay, so if now we do the same thing here, then we discover the following thing, a little lemma, that so this thing here, f is singular at P in Pn if, and so now let's look at, maybe I use T now just so that I don't have the same thing here. So P, so let me just, oh, actually, no, that's okay. Let's just leave it like this. If I just look at df dti at P is 0 for all I going from 0 n. So I'll just denote the variables for the projective space now, T0 up to Tn. and I just take the partial derivatives of this f. It's f. Okay? So as you can see, there is some kind of novel symmetry appears here, because here we had two different kind of equations. Here we have the same equation. The reason for this is very simple. It's just that we have the following equation. The point is that, remember, f is homogeneous of degree d. So, for example, you can look at, f equals t0, okay, t0, I want to say t0, t1 squared minus t1 squared minus t2 cubed, say. So this is some degree 4 polynomial. So there's a very easy way to express homogeneity, and this is the following. Well, we can just look at the sum, so the Euler equation, the sum of df dti to n, and then I just multiply, I need to multiply this by ti. So what happens if I just take the derivative with respect to, say, t0, I could just get this once, and t1, I get this twice, but altogether, I'll get 3 times this term, and the same thing here. So this is just, when you do this sort of operation, then what you really do is you recover f, because, I take the derivative to t0, but then I multiply by t0, of course, nothing happens. Same thing with here. Take respect to t1, I lose one t1, but I multiply back by t1. So actually, I recover each monomial back, and what you will get actually is a multiple, which is the total degree of the monomial. But since it's homogeneous, so we get all of them at the same time. So you just get d times f. Okay? So in this case, it's you will have, if you do this, you take t0, df dt0, etc., you'll just get 3 times f. Okay, so and so of course then you see that these equations are actually linearly dependent. So if you know all of these, that all of these things are 0, that will imply also that all of these things are 0. So that means f is also 0. So actually, these equations imply that in any local coordinates. You can easily see that. Okay, so it will follow from this. You need to check it a little bit, but it's easy. Okay, so you get something in projective situation. You get something much more symmetric, much nicer. Okay. All right. And now the exact same great thing happens as before, that it seems really very difficult to find. I mean, even this equation looks pretty difficult. I mean, even for this case, it's not completely obvious. So it seems really difficult to find, for a fixed pencil, say, to find how many of these singular elements there are going to be. But on the other hand, when we globalize this thing with the same trick as with the lines, then the thing becomes incredibly simple. So let's do that. So let's look at the universal singular hypersurface. So what do we do? So the only thing I'm going to do is I'm going to introduce an extra relation that I'm going to say I take a hypersurface, so I just take an equation, say like this, and I'll say that it should be singular at a particular point. Okay? So let's look at this sigma, which will be just some function f and some point p. So this pair now will be in, so it's a hypersurface and a point. So this will be, a point is in Pn now. And this is a hypersurface of degree d. Well, if you like, I can put the d here. It will depend on that. And so I just say the obvious thing is that xf, so this is the hypersurface defined. I always use this. Xf is just at P. Okay? So this is this universal thing. Remember, it's very similar to what we did before. Before we had a line, and then we said that that this line should be contained in some hypersurface. Now we just see that it should be there. And then let's remember what we did then is that instead of fixing F and counting, looking for P's here, what we did instead is we looked at the particular line or linear subspace, and we looked at all the F's that contained it. And so we do the same thing now. We are going to fix P now and look at, so this is pi 1, this is pi 2, Pn. So I'm going to fix now P, and I'm going to be interested in this fiber, P2 inverse of P. Okay, so what is this? And so of course what you see here is very simple. It's when you write down these equations, then you can see that these are just a set of linear equations again, just like in the previous case, on the coefficients of F. So if you let's just so the answer is here. The equations are linear, so this is just going to be codimension. So this is a codimension n plus 1, but that's not surprising because we agreed that we expect that we have n plus 1 equations, so this is really codimension n plus 1 projective space. Okay. And so this is because the equations are linear. So why that is kind of clear, because if you yeah, I mean you just write down df dt in the coordinates, you can easily check that. So let's just maybe take this. Where's my example? I erased it. Yeah, let's just take this example. So, for example, we have that, well, just a second. Maybe I didn't erase it. So let's maybe just do this one. Okay, so we have, sorry, there was a, let's just look at this. So as is ax squared plus bxy plus cy squared. Now let's calculate the two equations. So the two equations will just say that the derivative of at the point in x is 0, so that will be just 2ax plus by is 0, and the other is that 2cy plus bx is 0. And so the idea is that now we fix P, so we fix these elements here, and so then these are obviously linear equations for the coefficients A, B, and C. Now if you do a higher degree one, so you do A, say x cubed plus bx squared y plus etc. You do the next case, let's write down the equations again. Then what we get is 3ax squared plus 2bxy plus etc. equals 0. And the next one, and then you have some similar thing here. So if you take the y one, then this will disappear. So this will be 0 plus, and then you have just bx squared plus etc. will be equal to 0. All right, so the equation looks like this. So what you can see now is that, of course, once you do that, the degree in the point, in the coordinates of the point, will increase. So now the coordinates of the point, this is quadratic, 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 etc. But if you actually fix the point, So fix the values x and y, then in the coordinates it remains linear. You see, so the question we are asking, if I fix the point, fixing the point meaning the coordinates of the point, p is x, y in this case. Fixing the coordinates of the point, the equations in the coefficient remains linear, even though the other way around is much more complicated, then it's quadratic, okay? So when you fix the point, the equations are linear, and for that, and then it's simply, these equations are obviously linearly independent, that's easy to check, and so in this Pn now, for each point, you'll have a linear subspace of codimension n plus 1. Okay. So an immediate corollary is that this sigma is irreducible. And just like, I'm not proving it absolutely precisely, but it's not surprising, it follows actually from a general result, that if you, so now what is this sigma? This sigma is a Pn minus n minus 1 bundle over Pn. For each point P, we have a projective space of this sort. So it's not surprising that this is also smooth. So no matter how incredibly ugly this D could be, this sigma is actually has a very beautiful structure of just a projective bundle on a projective space. It's easy also to calculate its class. And of course, note that by definition, D is simply equal to pi 1 of sigma. Right? Since this is pairs where F is singular at P, and D is where F is singular somewhere, so clearly it's precisely this projection. Okay, is this clear? So a simple local calculation that maybe we'll get back to later, is not so important. So a local calculation shows basically it's sort of Bertini's version of Bertini's theorem, shows that a generic singular hypersurface has only one singular point. And so this implies then that generically this map is one-to-one, so it's called this birational. So that means the generic fiber, so that's the same thing, of course, of this map P1 restricted to sigma, mapping sigma to D, is a point, is one point. Right? So all I'm saying is that now I have pairs, variety, and singular point, and that's sigma. And of course, if for those varieties where there's only one singular point, when I project it onto D, then there's going to be one fiber. The fiber of this map, actually, so the fiber of this map of F is precisely the singular points. Singular points of F, right? Okay, so well, the corollary that we have here is that D is of dimension, so codimension. So what is the codimension of D now? Right? So let's calculate so the codimension of sigma was the codimension of each fiber, which was little n plus 1, right? Because it's little n plus 1 equations. So the codimension of sigma was little n plus 1. But then what I do is project sigma along an n-dimensional space so that generically it's 1 to 1. So that means there's exactly 1 dimensions left, is of codimension 1. Right? So it's precisely what we expect. Just like for the quadratic equation, you get one equation. So it's simply, there's a single equation, right? It's a universal, amazing single equation in the coefficients of the generic degree D polynomial, which will tell you if this polynomial has a singular point or not. And that's called the discriminant, of course. Okay? So this D is of codimension 1. And an extra interesting thing is that n is irreducible. Right? It's irreducible because it's an image of something that's irreducible. So sigma was irreducible because it was a Pn bundle, P sum bundle on P. So it's irreducible. We have something irreducible, its image is also going to be irreducible. So you have an irreducible codimension 1 thing in Pn, and so the equation defining this thing is actually called the discriminant, but it's not at all easy to find. I mean, even already in the quadratic case, it wasn't so easy to find, and here it's also not so easy to find. So the question we are asking a much less kind of complex question, and that's just what is the degree of D. So D is going to be equal to some psi equal to 0. This is the psi is the discriminant equation. I mean, it's identical to D. So e.g., it's like psi equals b squared minus 4ac for that other equation that we had. So this is very hard to find. So what we're looking for is just the degree question. So basically going back now, I just reformulated what we're trying to find. The same question at the beginning, it's a repetition, but what is the degree of psi? Okay, and so that's what we're discussing actually, was the degree of this psi. So we saw that there was 2 there, so let's calculate it. So I'm going to calculate this in several ways. Now maybe actually before we do that, let's just do some really very basic things, like very simple. Actually, let's try to guess this degree. So let's look at, so we are, again, just going back to the pencil situation. So let's take n equals 2, so that's the simplest, well, almost the simplest case. We had n equals 1, but that's really easy. And we are looking at plane things, and let's look at pencils. So it's always codimension 1, so that's kind of convenient. So we are always going to look at pencils, but pencils of things of different degree, right? So we're just going to look like pencils of things like that. And in this pencil, so in this family, we are going to search for the number of singular fibers, singular elements, okay? So first question, so what happens if D equals, well, D equals 0 is kind of boring, so D equals 1. Okay, so D equals 1 means that f is just a linear polynomial in 3 variables, right? So this is now n equals 2, so f and g are homogeneous polynomials. So f and g, homogeneous polynomials of degree d in 3 variables. Well, I can denote them by x, y, z, for example. Right? So suppose now f and g are homogeneous polynomials of degree 1 in 3 variables. So how many singular fibers you will have if you take all linear combinations of these? So you take 2 linear polynomials, so like 2x plus 3y plus 7z, and another one, you take all linear combinations. What happens if you take a linear combination? Well, what do you get if you take a linear combination? So you have like t0 times, and let's just look at example. Well, I can just, the simplest thing is let's choose f to be just x, that's a linear polynomial. And then other one is, let's it to be, I don't know, y plus z. That's a linear polynomial. Okay? So if you take a linear combination, you get another linear polynomial. So how many singular points does it have? None, right? It's a line. So you take a linear combination of 2 linear polynomial of homogeneous, you get another linear polynomial, and it has no singular points, right? So there is nothing. So actually, here the degree is 0. Okay, so there is none. No, there are no. Of course, we know this. I mean, there are no linear polynomials with singular points a priori. We already knew that, so that's not. So that's kind of irrelevant. But so let's look at the interesting case. That's why I want to show you. It's kind of beautiful. What happens if you take d equals 2? Okay, so d equals 2. Okay, so I'll now have to be a little more honest. So let's look at f and g. So that means we take 2 quadrics now, right? So this is degree 2 polynomial. So we take, say, a circle and a parabola or something like that. Okay, so let's look at a circle and a parabola. So over complex numbers, they have to intersect. So remember, it's Bezout's theorem says that they have to have 2 times 2, 4 intersection points. So Bezout says 4 intersection points. So this one of them is f equals 0, and the other is y equals 0. And now we take linear combinations. So as you can see now, of course, when you take linear combinations, the intersection points remain intersection points, because if, right, this is f is 0, and this is g is 0, this circle. So clearly, if you take a linear combination where both of them were 0, that remains 0. So those points remain in the same place. So no matter what element of the pencil you take, no matter what element of this pencil, the pencil is all linear combinations, every linear combination will go through these points. And so now we have to find singular things. Okay, so these two are not singular, but now we have to take singular things. So what would be a singular thing that you can come up with that goes through these 2 points and quadratic? So you need quadratic things that go through these 2 points. Well, hyperbolas are not singular. Singular is something. Yeah, that's right. So it's, well, nodes or whatever. Yeah, no, you're right, actually. Okay. It's not a hyperbola. It's a hyperbola with t equals 0. So yeah, so this is a hyperbola, xy equals t. And the thing when you degenerate it to 0 is when, that's right, no, not a hyperbola, it's a node. So that's this thing. So the only reasonable thing, actually, the quadratic singularity is this, xy equals 0. So this is what you want. So how can you construct these things so that they go through these these 4 points? Well, it's kind of obvious. I mean, it has to be a product of 2 things, right? So they have to be lines. So there have to be lines going through these 4 points. So there's not so many possibilities, right? So this is just all possibilities. I'm just going to draw one of them, but you can find, so one of them is obviously this one, right? So they're not going to be singular here, maybe that's a confusion. They have to be singular somewhere. But any two lines basically intersect. So you just take any lines that go through one point or another point, and this, well, you have to check that it's in the family, of course, but it's automatically, it actually turns out. Okay? So this is an example of a singular, it's singular here, a singular quadric in this pencil. So how many singular quadrics are there going to be in this pencil? Now this is a combinatorial question. 3, that's right. It's going to be 3, right? Well, it's just all pairs of things, because then I can also do this thing, and there's 3 ways of choosing, dividing 4 points into 3. There's 3 ways of dividing 4 points into 2 pairs, right? Because every time I do that, then there's another one, which is unfortunately the way I drew it. Of course, that's why you have to prepare, because then it's, of course, the other points are very far out. You know. Okay, my lines intersect here. They are skewed like that. Okay? So that's the singular point of this pair. And then there's a third one. So it's 3. Okay, so this is what we want to, so this is what we are after, was to generalize this thing. Obviously, when you start doing this, then this will become much more complicated as you go on. You can imagine cubics already, the cubics are already much more difficult, and this is precisely this question. The next one, the d equals 3, is the question we could not answer. We have to look at this, we have to understand this form, and this form is already going to be much, much more difficult. Here we're simply lucky because necessarily the singular element was irreducible. Oh, not irreducible, sorry. So it was a union of 2 things, and and then it was basically the same story as we had with the 2. You remember with this several component things like this. This we know how to calculate, and this is the same sort, right? We have 2 things. But you see here, it's going to be more difficult because now it's irreducible, and now we don't have these techniques. But now, with the actually, I can just do this now very simply. So let me show you, and then we'll, after the break, I'll elaborate. But it's really actually very easy now. Because you see, we have, what are we talking about? We're talking about just taking sigma, which is, again, so this is now, is a subset of Pn cross Pn. And we have lots of experience with that, so we have to just evaluate the class of sigma in this product, and then project sigma to Pn. That's what it is. So that's for just evaluate the class of sigma. And so the class of sigma is not difficult. One have to think a little bit, but it's easy to see. So first of all, what is the class of sigma? So there's 2 things we need to do. Just in the Chow group, in the Chow group of Pn cross Pn. So what is it? So actually, it's fairly easy. Because, as you remember, sigma is a complete intersection and is just given by sigma is an intersection of n plus 1 identical sort of equations. You remember those partial equations. And you remember that's why I did this example here. So what is the degree of the equation? So now you have to be a little careful. When you have degrees, what is the degree of this equation? So of course, when you have just Pn, it's easy. When you have a degree of equation, you just write on a polynomial. The degree of this polynomial is the equation. You have a single equation. But what is the degree of something in a product of 2 projective spaces? Well, then you have a bi-degree, right? So the equations look like, so if you have, say, I'll erase this just so that you see. So when you have product of 2 projective spaces, say, let's just say P1 cross P2, well, we did these things, but I just want to remind you, right? So then you have something, you have like T0, T1 here, of course, X, Y, Z here, and then an equation will have a bi-degree. So it could look like T0 squared times X cubed plus y cubed, and then plus, so it has to be homogeneous, so then it could be t0, t1, and then here you have another cubic polynomial xy squared, or xz squared, say, and maybe another term, but in any case, so you see what's happening. So a general equation that we can consider has to be homogeneous, because only those are meaningful in both P1 and P2, but it has a bi-degree now. So this is of degree 2 and 3 in this case. It has a double degree, a bi-degree. Right? So when you write down an equation in this thing, using the coordinates, it has a degree in the t variables and the x, y, z variables, and they're independent. So you have to record 2 degrees. Okay, and so what is the bi-degree of this equation? So you have to go back and see what happens. In one direction, it was linear, you remember, and that was the direction of the coefficients of Pn. So sigma was, remember, in Pn, I put that first, and then P little n. So in the first one, in the linear, you remember that's why it turned out to be projective spaces. It was just a linear equation, so it was just degree 1. And then when you do the partial in the other, you have to look at the other equation now. I mean, it's just the equation right in the part. And that was what, degree what? D minus 1, right? It was capital F. It was a degree D polynomial, so the x's, y's, etc., they had degree D, but when you do a partial derivative, the degree decreases by 1, and so you just D minus 1. It's easy to check again. So you just write down those equations, and you will see that's precisely what you get. This is just what I mean is this is the equations were like df, dti. I mean, you just write them down. It's obvious that that's what you get. So there are now equations both in t's and the coefficients of the f's. So you think of as equations in both two sets of variables like this. You'll see that degrees are precisely that. Okay? I'll just take one more minute to finish this because now it's really easy. So we found, so what is the class? Now they are just intersections, transversal intersections of these things. So in our Chow group, we just take the products of this. So if I now here use the fact that the Chow group of Pn cross Pn is just some, so I introduce two variables, say alpha here and psi here. So alpha is the generator of this, psi generator of this, and I divide this by the usual relations that alpha to the n plus 1 is equal to 0 and psi to the little n plus 1 is equal to 0. That's our usual way of describing the Chow group of projective space. And so now the class is in the Chow group is given by, we can write it this way. We just take this class. So this class is now an alpha and d minus 1 psi. We raise this, and now we take this n plus 1 times. Okay? So this is a class. And then we just need to find the degree of the projection. So now what does it mean that you look at the projection? Well, the projection means that you look at the intersection with a line that's in this so the projection now what is the degree of the projection? Pi 1 of sigma of d equals pi 1 of sigma, projection to this thing. And it's easy to see it's so I claim that this is the coefficient, I'll just give you the answer, of sigma of this polynomial in front of alpha times psi to the n. Okay, because if you think about it, what this means is this precisely means that you take a linear family, and this means that you take a point anywhere on Pn. Okay, so you need to, I just don't, maybe I can explain a little better after the break, but anyway, this is easy to see. That's precisely what it means. This means a singular point anywhere, and this means a linear in Pn, and this means just take a linear family of the thing. And if you do that, then you can easily see that this is equal to precisely, well, alpha. So this is actually the very last term here, where you take psi to the n. So psi to the n plus 1 actually is 0. So that doesn't exist. So psi to the n, and then alpha. So this is just the binomial form is n plus 1, choose, say, 1, times, this is the last term, times d minus 1 to the power n. So this is just n plus 1 times d minus 1 to the power n. Just give me now just 20 seconds. So then let's just check finally what we wanted. So n equals 2. So the plane situation, we get the degree of d is equal to 3 times d minus 1 squared. So if d is 1, this gives me 0. If d is 2, that's 3 times 1 squared. This gives me 3. And if d is 3, it gives me 3 times 2 squared. That's 12. Okay, so we recovered brilliantly our d equals 1 equals 0, you know, the lines, d equals 1 equals 3, that's the picture over there. And we also got the answer for, we were missing for plane cubics, which is this. So in a generic family of plane cubics, there is 12 nodal cubics of this form. Okay? All right, let's take 15 minutes. I went over time, I will take 15 minutes. Okay. So let's continue. Yeah, so I just wanted to make a quick remark about this calculation, right? So what does it mean in order to find, again, why this is why is this true? Right, so why do you need the coefficient of alpha psi to the n? So you just have to think about what we are really looking for. And I mean, one way of thinking about is what does it, we would like to intersect is to find the degree of d, to find the degree of d is going to be just the top degree, so the degree of a sigma intersected with, so this degree of d is slightly different place. So d is, remember, is just in Pn. Now I am sigma is in the product. So it's degree of sigma intersected with what? So it's intersected with a line and in the Pn direction and in an arbitrary, so we are looking for the case when the single point takes place any place in Pn, because that's what we are discussing, right? That we're looking for in a pencil where there is somewhere a point. So this means it's a line in Pn and so I have to continue here, line in Pn and a complete fiber in Pn. And so that precisely means to take this coefficient, or put it differently, it's the same thing as if I want to, sorry, it's a little disorganized now. But this is the same thing as just the degree of sigma intersected with the dual of this object. And the dual is just alpha to the n minus 1 times nothing. So because everything is this. So if you think about it, it's the same thing. So the degree of this, and the degree by definition is the top coefficient, right? So the degree of the coefficient alpha to the n, xi to the n. Okay, so you need to think a little bit about that. Okay, so the last thing I want to explain today is how to generalize this in various directions. Maybe an alternative. So now what the plan is, I'm going to define a slightly more general thing and rederive the same formula, in fact. So this is the plan now. I'll leave that. So let's see. So the idea is the following. It's called the principal part of a function. Now, this is sort of an ancient deal, and actually it's completely universal, so this also makes sense in differential geometry. In maybe it's even better to think a little bit, in my view, think about this in differential geometry, okay? Because, so the question is simply the following. Suppose you have a manifold M, is a manifold, and then you have F, M, well, you can even think of it this, some smooth function. So, and I just want to understand the behavior of this function at a point. So this is some really simple setup, but there's already a question here. So most certainly, so what is sort of invariant things I can define here? What is that I can understand out of the behavior of F? And so there is one obvious thing, is that I can say, you can ask me what the value of the function is. So F at P is certainly well defined. Well, it's not even clear what I mean by this probably, but you'll see in a second. Is well defined. I mean, I can tell you what F of. Why well defined? I mean the following, though, is that, of course, normally we think of functions in local coordinates, and those local coordinates can change. I can change the local coordinates some other thing. And then, of course, so well defined, I mean independent of coordinates. Independent of coordinates, of course, if I choose, no matter what coordinate I choose around the point P, the function f at that point will have the same value. That's clear. Okay? But now I can ask the following thing. Well, clearly, after having chosen coordinates, given coordinates near P, I can write f will go to a function of this sort, so it will be just the constant part, f of P. Then there will be a linear part, so I'll choose them to be x1, xn, the local coordinates. And I assume near P, I mean that when they're all 0, then that's exactly the point P. So there will be a constant term, right? And that's NP. And then there's a linear part. And those are given, of course, by sort of partial derivatives. So, but I will not denote them by anything right now. So it's just sum of AI xi plus the quadratic part, sum of bij xi xj. Well, there's some other monomials, but it's not so. I mean, it's supposed to be some xi squares as well, right? So you can think of bij as being a symmetric matrix anyway. So this is how you write down polynomials. So the question is, which is not so trivial, is what is precisely well defined now? Like, is the linear part basically well defined? Can we give sense to some reasonable way to the linear part of this, or the quadratic part? Okay. Now, this is not so easy, in fact. For example, I mean, the simple question, can I make sense of the statement that the linear part vanishes, or something like that? That's a reasonable statement, right? Or yeah, something of this sort. Okay? And so the answer is that in complete generality, in fact, the generality that we are interested in, actually this is not well defined. So we cannot make sense in general of the linear part. So the linear part is not defined in general. Well, you'll see in this generality it is, but in in complete generality, well, actually, maybe I'll write down right away what we are going to be interested in. Because, of course, remember, in reality, our function is, now in our setup, is defined not as functions, but as sections of line bundles. We take Pn, and then our polynomials, homogeneous polynomials, are actually sections of line bundles. They are not actual functions. So in our setup, we need a slightly more general thing. We need to understand the following thing. So we have this manifold M, and we have this L, which is now a line bundle. And then again, I can do the same thing. I can define things in local coordinates, so I can now look at sections. So F can be sort of as a section of the line bundle. But again, I mean, the only real interesting example we're thinking about now is just homogeneous polynomials, which are sections on Pn, right? So this is the example we have in mind. Here we are trying to understand what these parts are. And so in this setup, the same thing works. You have to trivialize the line bundle locally, and then you can ask then it still you will be able to write things down this way. And I mean, we know how to do that. You'll do an exercise writing down the function in different linearized coordinates, and then you can ask these questions. And the answer is that no, they are not completely well defined. But there is something that is well defined, and this is what's called the principal part, and then the parts of sort of higher vanishing. So, I mean, what is well defined is the following. So we clearly have, how can I interpret this silly thing here? Now with values in a line bundle, it's the following thing is that you can take just O, so now we think of just, this is a sheaf of functions, or a sequence of sections. So let's call this O of L. It's not a very good notation, but anyway. Of L. And then, of course, near P, near this point P. And then at that point P, obviously, you can evaluate that section, and you have LP, and then you can look at what the kernel is. And what is the kernel? So the kernel is the, so in general, you can just look at, if you remember this, at MP tensor LP, where these are just the functions vanishing at P. So again, what is really well defined is the function vanishing in P. So if you don't want this L, we can just think of locally now without L. It's just you just look at the sheaf of functions. You can evaluate that function. So I'll just, so here L trivial. It's a special case. You will evaluate that function. See, the kernel of this map is well defined. And those are the sheaf of functions that vanish P. So this is the kernel. And of course, we just denoted usually this by MP. It's the maximal ideal in O near P. Okay, so this is well defined. And then, of course, we know that what is also this is a completely well-defined thing, so I can take the square of this now. So these are squares. So what I mean by this, these are squares, or products of two functions vanishing at P. That's what this is, right? So these are basically quadratic polynomials. And now if you look at that, then here you have a quotient now. So what is this quotient? This quotient we call the principal part. So first principal part at the point P. So this is certainly well defined. So again, what is meaningful somehow is the principal part of the So the principal part of a function near a point. This is well defined. And now what we have, of course, that if I have know the principal part, so the principal part is sort of locally described this way. Now, of course, I can evaluate this now. So there's a map from here to just the fiber this, or I can tensor then later this with a line bundle. So it doesn't matter. And what I have that, of course, coming from these two equations is that this is just so these two equations, sorry, this is a little bit confusing now, but so I started this without the L, then I explained the L because that you need that too, so that it's not, that thing is not well defined, so that's a little confusing. But anyway, I went back now to a situation without L for simplicity. Okay, so finally we get an equation like this, and what is m over m squared? So we discussed this before, so recall that this is all happening on a smooth, actually this works in any differential geometric setup, but now go back to the algebraic situation, then mp divided by mp squared, this is just the dual of the tangent bundle of m at the point P. Right, and so this is quite clear because so MP, remember MP itself is just a certain function vanishing there, and obviously if you have a tangent vector and you have a function vanishing at a point, then you compare them to get a number. So this is precisely the dual of the tangent bundle. So you can write it this way as well. But the point is that finally, I know this is a complicated thing, but the point is that this exact sequence, so let me write it this way. Well, now I can just globalize it, so I will just write it globally this way. And now I don't put the P here, so now this is there's a general bundle like this. So we globalized. So by globalizing here, I wrote down what happens at a single point P. These are just vector spaces now at single point P. This is a finite dimension like this and this. And now I just look at the whole manifold, and they glue together to bundles. And so this is then the trivial bundle. And this is the bundle of principal parts, and this is the kernel. So we get this vector bundle does not split. This does not split. So what I mean is that vector bundles, it's not true that the principal part is equal to, is isomorphic as bundles, say. There's no way to. So in the principal part, there are the parts of the functions which vanish at the point, but there's no way to find to have a projection in the other direction. Okay, so again, we can tensor this with L if it's necessary. Part at L, and this is then it's just L. Then you just write it down once more. So this is the general case when the value of the function is not in a constants, but in L. Okay. Anyway, this is not so crucial that it's not well defined. You'll have a little exercise to do, and then you'll understand what this means. I mean, what is true, however, is that we can continue this, so we can write more generally. We can also write higher principal parts. So you can have principal part M of mapping to principal part m minus 1. So if we know the function up to degree m, we also know the function up to degree m minus 1. And here you'll have then the symmetric power of degree m of t star of m. Okay. So let me just, it's better to understand this in some applications, but let's just do the calculation now using this, the calculation of degree d using this technique. So what do I mean by using this technique? So first I need to So I'll ask the same question. So we go back to our same question. Same question. But it's put in this more invariant language. So you see why. So now let's assume that f and g now are degree d homogeneous polynomials. But remember, what that is just sections of O of d, if you like, or as a sheaf or as a bundle is just you remember we have the usual sequence of Pn. You have the subbundle going to this V, which is just Cn plus 1, and then to the quotient bundle. This is a line bundle, and this is then the quotient bundle, right? So from this point of view, then this is just S star to the power D, right? These are linear functions of dimension. So let's look at this situation, and then we are trying to see the following thing, that we would like to understand, remember which when question was when T0 plus T0F plus T1G is singular at some point P. So I will formulate this thing now in the language of these principal parts. So the idea is the following. So first of all, if I have a function f, then from this sequence here, if I have a function, then I know its for degree 1 principal part. So if I have a function f, which is a section here, then this will actually give us a section tau f, where at every point on Pn, now I tell you what the principal part of the function f is at that point. So that will be just the principal part of, at this bundle now, of these functions with values in this bundle of degree 1. So you see, instead of, I mean, if you take a section, then just at each point, you just say what the value of that section is. But you can go a little further, that's what I'm saying. At each point, I'm going to tell what the value of the section is and also what the first degree approximation is. So remember here, it follows easily from here that the dimension of this principal part is n plus 1, right? So the rank, so this is the vector bundle now, the rank of PR. Well, this is independent of that. 1 is equal to n plus 1. So at each point, I tell what the constant term is and what the linear parts is. But I do this somewhat invariantly because you cannot separate the two. That's the idea. Okay? And so now the calculation, oops. I don't use this, but I see here. Okay. So the calculation then is precisely the following, that we are looking for We formulate the situation somewhat more differently, and this will be in complete analogy now what we were doing for the lines for looking for the lines. Remember, when we were looking for the lines in subvarieties or hypersurfaces, what we were doing is that finally we defined a bundle on the Grassmannian, which was a bundle of restricted homogeneous functions on the tautological bundle, and it was a zero section of that bundle that gave us the correct answer. So we had a top Chern class of a bundle, and this is how we found so let me just write this down. In analogy with the degree of the set of lines, of the Fano variety of lines in the Grassmannian, now we do the same thing. Grassmannian set of lines on a hypersurface. Grassmannian. We will represent now the singular locus in Pn. We would like to now do the following. I fix this f and g, and I would like to find the points, the set of points P in Pn, which are such that for some T0, T1, so there exists a T0, T1, a T0 F plus T1 G is singular at P. Okay, so this is what I'm asking. And the point is that because we know that generically every hypersurface has just one singular point, so in fact this number will calculate the degree. So generically, this is the degree. Because we're trying to count hypersurfaces. What I'm doing now is slightly different. I look at the family and I count all singular points. But since each singular hypersurface generically has only one singular point, so this will actually count the number of singular hypersurfaces in the pencil. Okay, that's the idea. So it's a little clever. But anyway, this is just much more, this method is just much more general then. And so then the calculation here from here is easy. So you just, okay. So then, yeah. So then what is that we need to do now? So this, however, what does it mean that the point is singular? So what does it mean? A point P is a singular point of some f if the principal part of, so did I write tau f here already? Yes. So if tau f, I can just write it here, if tau f at P is 0. So this is, of course, what those equations are precisely the same. Going back there, so now if I go here, so this means, now what does it mean that for some T0, T1 this is true? Well, how could this happen? It's just if T0 tau f plus T1 tau g is T0 T1, such that T0 tau f plus T0 tau g, T1 tau g, is 0 at P. This is precisely true if Tf at P and Tg at P are linearly dependent, right? That's the same thing. So Now we have a rank n plus 1 bundle, and we are looking for the locus when two sections are linearly dependent. And so this is then given by, Cn, so one less. So Cn plus 1 would be when one section vanishes, and when two sections are linearly dependent, that's given by Cn of this bundle PR to the power d. Okay? So this is now a class, a Chern class in Pn of a certain bundle that we're calculating. And now we just use Whitney's formula, and we immediately get to the thing. Just give me one more minute. So you remember our basic formula. So now we do the calculation of this Chern class. So we need to calculate the Chern classes of this PR, the total Chern class of PR, in fact. So what we're going to do is we use the formula that T Pn, right, is equal to Hom SQ. This was our basic formula, right? So this is just S star Q, tensor Q. And so that means that T star Pn is equal to S times Q dual. And yeah, so then the point is that we can do the following. So maybe here, the usual thing we do is that I tensor this with S. So we have the fundamental equation. S, V is the trivial bundle Q. So this is just Cn plus 1. So then I tensor this as dual. So then this leads to S, so the trivial bundle, so say O, I tensor with S dual V times S dual Q, which is just T of Pn. I dualize this, I get T star Pn, and then I dualize everything S V dual, but that's the same. It's a trivial bundle times just O. And then I just needed to take the tensor product of this with L, if you remember. So I just get L times T star. So L, sorry, this is S star to the power D. This is our line bundle now. T star Pn goes to S star. Here I have D minus 1 times V. And here I have S star D. Okay, so sorry, this is now a little too quick, but so you just do these manipulations. And the point is that if you look at the equation that I already raised for PR, then PR fits into the very same sequence. If you remember, PR1 with values in this line bundle goes precisely satisfies precisely this condition. Remember, the subset was the cotangent bundle tensored with this, and then you could evaluate you took a section of this bundle, you could evaluate the bundle, and the kernel was precisely this. So this is kind of amusing. You have two bundles, this bundle, the trivial bundle times S star D minus 1, and this bundle, which have the precise exact same, they fit into the same exact sequence, but they are not isomorphic. So they are not isomorphic, but they fit into the same exact sequence, and for Chern class calculations, you get the same thing. So for that reason, I mean, just now really it's just 1 minute. So because by Whitney's formula, that means that the total Chern class of this PR1 S star D is the same as the total Chern class of, and now what that means is that you just tensor this line bundle, the trivial bundle, that you just take this many copies of it. So this is just S star to the power D minus 1, and then you just take this, this n plus 1 times the dimension of of this bundle V. That's what this means. Okay, and so then by Whitney, this is just the total Chern class of this to this power. So the total Chern class of S star is just 1 plus d minus 1 times psi. And now you raise this to the n plus first power. This is it. And now you need to take, again, Cn of this. So this means the degree n component. So Cn of this is just equal to n plus 1 times d minus 1 to the power n to psi to the n. And that's precisely the form we had before. Oh, sorry, and d, yeah, this is correct. Yeah. Okay. So, and now then this method you can use to calculate some more general things. Maybe just one last word, but this is not technical, is that you can then ask the following question, just for plane curves, say. Is the exact same question, but you can ask what is the locus when you have two nodes? Okay, so you can start calculate degrees. You go you go higher and higher degrees. So question. So that the degree of the variety, let's call it, I don't know, n. That's a bad notation. QD, where you have Q, QD, where there are two or maybe 3, 4 nodes. So now what we calculate is the subvariety where you have one node. But so every time you impose more nodes, the codimension increases by 1. And you can ask what that is. And this is what I'm working on, but this is like one of the central problems in numerative geometry is to give a formula for this. So this is still unknowns if you have several nodes. So what I'll try to explain next time is actually what the methods are, and then we'll actually do the calculation for rank for maybe 2 nodes and maybe even 3 nodes, and then you'll see how this works. But this is a very active area now. Okay.